A black dwarf is a white dwarf that has sufficiently cooled that it no longer emits significant heat or light. Because the time required for a white dwarf to reach this state is calculated to be longer than the current age of the universe, no black dwarfs are expected to exist in the universe yet, and the temperature of the coolest white dwarfs is one observational limit on the age of the universe. A white dwarf is what remains of a main sequence star of low or medium mass, after it has either expelled or fused all the elements for which it has sufficient temperature to fuse. What is left is then a dense ball of electron-degenerate matter that cools slowly by thermal radiation, eventually becoming a black dwarf. If black dwarfs were to exist, they would be extremely difficult to detect, because, by definition, they would emit very little radiation. They would, however, be detectable through their gravitational influence. Because the far future evolution of stars depends on physical questions, such as the nature of dark matter and the possibility and rate of proton decay, which are poorly understood, it is not known precisely how long it will take white dwarfs to cool to blackness, a section IIIE, IVA. Barrow and Tipler estimate that it would take 10–15 years for a white dwarf to cool to 5K. However, if weakly interacting massive particles exist, it is possible that interactions with these particles will keep some white dwarfs much warmer than this for approximately 10–25 years, a section IIIE. If protons are not stable, white dwarfs will also be kept warm by energy released from proton decay. For a hypothetical proton lifetime of 1037 years, Adams and Laughlin calculate that proton decay will raise the effective surface temperature of an old one-solar mass white dwarf to approximately 0.06 K. Although cold, this is thought to be hotter than the cosmic background radiation temperature 1037 years in the future, a section IVB. The name black dwarf has also been applied to substellar objects that do not have sufficient mass, less than approximately 0.08 Ma per mil, to maintain hydrogen-burning nuclear fusion. These objects are now generally called brown dwarfs, a term coined in the 1970s. Black dwarfs should not be confused with black holes or neutron stars. Future of the Sun: once the Sun stops fusing helium in its core and ejects its layers in a planetary nebula in about 5 billion years, it will become a white dwarf and, over billions of years' time, eventually will no longer emit any light. After that, the Sun will not be visible to the naked human eye, removing it from view. The estimated time for the Sun to cool enough to become a black dwarf is about 10–15 years, though it could take much longer than this, if weakly interacting massive particles exist. See also, degenerate matter, heat death of the universe, references.